Hello and welcome to this description of how to configure the STM32H5 to develop a trusted firmware for Cortex-M, also called TFM. The TFM framework is composed of a secure boot and secure firmware update application executed after reset and a set of secure services available at runtime. MCU boot is a root of trust and is immutable. It's the first code executed after each reset. A non-secure application and part of secure application can be updated via the MCU boot application. The TFM core manages the PSA Level 2 isolation inside the secure application and controls access to the secure services from the non-secure application via the PSA APIs. The following secure services can be requested by the IoT application: crypto services, secure storage, and attestation services. TFM is modular. Each gray box can be deactivated independently via compilation switches so that secure services can be easily reduced to only keeping the MCU boot part. Secure crypto services can be configured to only support the crypto algorithms needed by the application. TFM core and TFM secure services are used for STM32H5 PSA Level 3 certification that includes resistance against physical attack in addition to PSA Level 2 certification requirements. They are based on the hardware protections provided by the STM32H5 series, referred to as TBSA-M hardware in the figure. TBSA stands for Trusted Base System Architecture. A device deployed in the field operates as an untrusted environment and is therefore subject to threats and attacks. To mitigate the risk of attack, the objective is to run only authentic firmware on the MCU. The secure firmware update relies on a server providing the encrypted firmware and secure boot and secure firmware update or SBSFU service available in the MCU. The OEM server and web services are responsible for storing the new version of the device firmware and communicating with the device and sending the new image version in encrypted form. The STM32H5 is deployed in the field. It embeds a code that runs the firmware update process. It communicates with the server and receives a new firmware image, authenticates and decrypts it, and installs the new firmware image before executing it. The TFM Secure Storage or SST service implements PSA-protected storage APIs. The service is supported by hardware isolation of the flash access domain and relies on hardware to isolate the flash area from non-secure accesses. The current design of the SST service relies on the hardware abstraction level provided by TFM. The SST service implements an AEA-D encryption policy based on AES-GCM as a reference to protect data integrity and authenticity. The design also meets the following high-level requirements: confidentiality, resistance to unauthorized accesses by hardware and software attacks, access authentication, mechanism to establish the identity of the requester, integrity, resistance to tampering by the normal users of a product, package, or system, or by other physical access to it. If the content of the secure storage is maliciously modified, the service is able to detect it. Reliability, resistance to power failure scenarios and incomplete write cycles. Configurability, high level of configurability to increase or decrease the memory footprint to cater for a variety of devices with varying security requirements. Performance, optimized for use in resource-constrained devices with a very small silicon footprint, the power, performance, area, or PPA should be optimal. The TFM Internal Trusted Storage or ITS service implements PSA Internal Trusted Storage APIs that can write data in a microcontroller built-in flash memory region that is isolated from non-secure or unprivileged applications by hardware security protection mechanisms. The design also meets the following high-level requirements: confidentiality, resistance to unauthorized accesses by hardware and software attacks due to hardware isolation of the flash access domain, access authentication, mechanism to establish the identity of the requester. Integrity, resistance to tampering by attackers with physical access is provided by the internal flash device itself, while resistance to tampering by non-secure or application updatable IoT attackers is provided by the hardware isolation mechanism. Reliability, resistance to power failure scenarios and incomplete write cycles. Configurability, high level of configurability to increase or decrease the memory footprint to cater for a variety of devices with varying requirements. The TFM cryptographic service provides an implementation of the PSA cryptographic API in the PSA updatable ROT secure partition in TFM. It's based on Mbed Crypto, which is a reference implementation of the PSA cryptographic API. For more details on the PSA cryptographic API or the Mbed Crypto implementation, refer to the Mbed Crypto GitHub repository directly. The service can be used by other services running in the Secure Processing Environment or SPE, or by applications running in the Non-Secure Processing Environment or NSPE to provide cryptographic functionality. TFM Initial Attestation Service allows the application to prove to a verification entity the device identity during an authentication process. The Initial Attestation Service can create an Entity Attestation Token or EAT on demand, which contains a fixed set of device-specific data. The device must contain an attestation key pair, which is unique for each device. The token is signed with the private part of attestation key pair. The public part of the key pair is known by the verification entity. The public key is used to verify the authenticity of the token. The data items in the token are used to verify the integrity of the device and assess its trustworthiness. The provision of the attestation key is beyond the scope of the attestation service and should take place during the manufacture of the product. Following are the main security configurations available on the STM32H5. The STM32H5 7X security implementation supports all the steps of the secure boot: reset, immutable root of trust, updatable root of trust, secure and non-secure applications. The STM32H5 6X security implementation only supports an OEM IROT. This corresponds to the intermediate part of the figure. The STM32H503 does not support trust zone. This case corresponds to the bottom part of the figure, also relevant when trust zone is disabled on STM32H5 7X and STM32H5 6X. When trust zone is enabled, either the STI-ROT or OEMI-ROT is executed after the reset. In both cases, TFM can be used as the foundation of the secure image. Therefore, TFM can still be implemented on STM32H5 devices. The possible paths to TFM implementation are colored in pink in the figure. Either executing the STI-ROT and then an OEM UROT that launches TFM on the secure side. The OEM UROT can also be executed after the OEM IROT. Secure Manager is the new strategy of the STM32H5. The TFM approach is changed versus the STM32U5 solution. The STM32H5 security model is represented on the left. The STM32U5 security model is represented on the right. The main benefits offered by the Secure Manager are easing security integration, enhancing ST security offer, and delivering validated and certified security solution. Due to the Secure Manager new offer, we're changing the TFM approach. The TFM delivery management will be done in a different way on STM32H5 compared to STM32L5 and STM32U5. For STM32L5 and U5, the TFM source code is delivered in cube package STM32Cube TFM. For STM32H5, the TFM source code will be upstreamed directly through the external TFM GitHub. Then, STM32Cube H5 TFM will embed only a binary corresponding to the upstreamed version. The STM32 Trust T Secure Manager encompasses two types of packages. the STM32 Trust T Secure Manager Access Kit, or SMAK, and the STM32 Trust T Secure Module Development Kit, or SMDK. Easy to be installed into STM32 products by the customers on their production lines, the STM32 Trust T Secure Manager Access Kit, or SMAK, offers a ready-to-use, high-performance and certified solution to support the secure boot, root of trust, cryptographic, internal trusted storage, initial attestation, and firmware update functions as defined by the ARM PSS specifications. Thank you for attending this presentation.